Okay, this is Module 4, Lesson 2. In this lesson, we'll continue our discussion of magnetism, where we're going to be focused on magnetic domains. In last lesson, we talked about several types of magnetism. We say all the materials have diamagnetism, and then we say some materials are ferromagnetic. In this lesson, we'll mostly focus on ferromagnetism. One thing that's quite different between ferromagnetism and diamagnetism is that each of the magnetic ions inside your ferromagnetic material would actually have a spin. And these spins are typically randomly oriented in the case when there's no long-range order. And this is what we call ferromagnetic case. And then when you apply an external magnetic field onto the system, you would imagine all the ferromagnetic moment will start to be aligned, corresponding to the same direction of the external magnetic field. And this is what we call when the systems are completely aligned with respect to the external magnetic field, and this is what we call induced ferromagnetism. And there's also a case of spontaneous ferromagnetism. In a spontaneous ferromagnetism, as you gradually cool the system from paramagnetic to ferromagnetic case, and then the system will spontaneously order into a preferred direction. Typically, this is what we call the easy axis of a ferromagnetic long-range order. However, since you do not have an external magnetic field applied onto the system, the preferred orientation direction can be different for different domains. Therefore, even in the ferromagnetic case, you may or may not have a total external ordered magnetic moment if you simply, by picking it up. So that means in the case of a ferromagnetism, what actually happens is you have many, many different domains, and on average, these domains will actually cancel out the total magnetic order moment. What happens is then, if you apply an external magnetic field, instead of inducing a moment, you actually align these moments together so that eventually all the different domains would be aligned in the same direction. And in the case of no external magnetic field, and these domains are aligned in different direction, and the separation between domains is what we typically call domain walls. So in the case of a paramagnet, as I said earlier, the system has no long-range order. That means the spins are completely randomly oriented. So if you measure the susceptibility, or in the inverse susceptibility, if you gradually measure the temperature dependence of the inverse susceptibility, that means H divided by M, and your paramagnetic susceptibility would actually goes to 0, or the inverse susceptibility actually will goes to 0 at 0 temperature. So that means there's no spontaneous magnetization in the paramagnet. And in the case of a ferromagnet, on the other hand, as I mentioned earlier, that the system actually orders below a characteristic temperature, which what we call Tc. And this is called the Curie temperature. And below such a temperature, the system actually prefers to have a moment aligned along the same direction. And this is what we call a ferromagnetic long-range order system. And in such a system, if you actually do the temperature dependence of inverse magnetic susceptibility, what you actually will find is that the intersection of this inverse magnetic susceptibility actually occurs at characteristic temperature, which we call theta. And in such a case, then you'll have an intersection of a ferromagnetic susceptibility approaches 0 at a degree theta, in the case of 1 over chi. And this is clearly different as compared with the case of a paramagnet. So what is actually a domain wall? A domain wall is a system in which you have many small regions of the sample that are ferromagnetic. But the magnetic order moment of different regions are actually aligned along different directions, such that the total magnetization of the system is actually 0 without the applied external magnetic field. And this picture illustrates quite clearly what is actually a domain wall. For example, in such a sample, you have some samples in which the moment align along this direction, whereas others are aligned on a direction that are 90 degrees from this direction. And the edges of the domains are what we call the domain wall, and the width can typically a few hundred atoms wide. The reason the system actually prefers to form a domain wall is because when you do not have external disturbance, there's really no preferred way for any particular domains to form. I mean, it typically depends on the defect in the system, and that means the total magnetization of the system is actually 0 in the case of no disturbance of external magnetic field. Now, let's imagine we're gradually applying an external magnetic field to a system that form a different domain walls. Of course, we know when we apply enough large of a magnetic field, all the domains will gradually be aligned along the magnetic field direction. And let's imagine in our initial case, we're at 0 external magnetic field. As we gradually increase the size of the magnetic field, what we will find is that gradually each of the domains will be aligned along the direction of external magnetic field, and eventually all the moment will be aligned along the field direction, and then your domain wall actually will cease to exist. And in this case, as you gradually crank up the field to the other direction, and then eventually you'll form this so-called hysteresis loop, and in which you will see the size of the domain will change from A to B, and then from B to C, and then finally from C to D, and then finally from D back to A. So this MR is what we call remnant magnetization. MS is what we call the saturation magnetization, and then HC is what we call co-civic field. So what this maximum magnetization indicates is that when the applied field is large enough, you would have aligned all the moment along the field direction. That means if you continue to apply additional external magnetic field, there will be no more moment increase because all the moments have aligned already. As we said earlier, because the moments are localized along each of the atomic site, any additional applied magnetic field will not change the magnetization anymore. And one can ask the question, is this also the case in the case of a diamagnetism? That means whether one can saturate a diamagnetic signal. And the answer is one cannot, because in the case of a diamagnetic signal, doesn't matter how much external magnetic field you apply, you always induces additional current of these current loops. Whereas in the case of a ferromagnet, when all the moments are aligned by the external magnetic field, and then the magnetization actually saturates. And that's one of the key differences between a diamagnetic signal and ferromagnetic signal. So how does domain actually moves? Initially, when you apply an external magnetic field onto the system, the domain moves in a reversible way. This is what we call the reversible wall displacement. As you gradually apply more magnetic field onto the system, then system becomes irreversible wall displacement, and then you finally have domain rotation in which all the domain flick into the same direction. And that means at that case, then all the moments are aligned along the field direction. Let me use a picture to illustrate what actually happens. So in the case of a zero field, let's imagine you have a situation like this, where all the moments are aligned randomly, saying typically like this. As you initially apply external magnetic field, and some of the domain wall, for example, this one, will move slightly in the so-called reversible wall motion. As you gradually apply more magnetic field, and then you change it into irreversible wall motion, and then finally you will rotate magnetic vectors so that all the moments are start to be aligned in the same direction. And this is what we call the saturation moment of the system. And the equivalent illustration is shown here. So the direction, always the direction of the magnetization direction is always going to be the same direction as the external applied magnetic field direction. So the irreversible domain wall motion typically is due to the fact you have impurities in the system. The motion of domain wall from a defect is not reversible when the field is actually reversed, and as illustrated in this picture. As you gradually apply magnetic field, and when you have a defect, and then you have a situation like this. But then when you apply field in the other direction, and then you would have a situation that is not symmetric with this situation. So this is when you have irreversible domain wall motion. So in the case of a ferromagnet, as we said, you can gradually, in the unmagnetized case, the total magnetization is 0, and then you can apply magnetic field, and you have this so-called domain growth, And then finally, you can completely magnetize the system when the system form a completely aligned system. So the size of the moment, the size of the field you will need to saturate the moment direction is called the saturation field. And then depending on how well or how much you will need to go through this hysteresis loop, and this is, you can have a high field needed for this, and then low coercivity field needed for this. And then for really soft ferromagnet, you'll have no remnant magnetization at all. And that means as soon as you turn off the external field, the system becomes completely random. So this will be what we call the soft ferromagnet materials. And this is what we call the low coercivity magnet. And this is what we call high coercivity magnet. And these will have different applications, as we shall discuss in our following lessons.